Okay, so in today's session, I will be going through the gas turbine assignment, which was assignment number 4, the problems of this assignment number 4, and the the recently assignment number 7. So the problems, I will not be discussing the problems directly, but I have solved the problems and I know the theory which would be required in solving those problems. So I have devised the theory in my presentation such a way that you will find it very easy to solve the problems. Okay, so I think the deadline is not yet, it is yet due now, so it is not yet completed. So you will be having some time to solve the assignments and check the means correlate with the theory that I will be presenting. So once again, I welcome you to this problem solving session. I am Tanma Sharma, TA of this NPTEL course, Power Plant Engineering, and let us start today's session. So, in assignment number 4, question 2 was like this: that impulse turbine with a diameter of 140 centimeter runs to 2500 rpm with, if the blade velocity blade speed ratio is 0.48, then the inlet velocity of steam will be. So it is a very simple problem. The answer is something like this. So first the blade velocity will be calculated, as we know the diameter and the rpm. So this is the blade velocity. Velocity ratio is given to be 0.48, so directly we will get the inlet velocity of the steam, that is 381.6 meter per second. Then the next problem in assignment 4 is the optimum pressure ratio for maximum specific output for ideal gas turbine plant operating at initial temperature of 350 Kelvin and maximum temperature of 1100 Kelvin. So we are given the initial temperature and the maximum temperature of the cycle, which basically means that this is the initial temperature at which it is inlet to the compressor. This is the maximum temperature it can be attained after getting the heat from this combustion and before entering to the turbine. So the relations for this optimum pressure ratio stands like this, that R P2 by P1. So this is the P2 curve and this is the P1 inlet to the compressor. So this relation holds like this, that T max by T min to the power gamma divided by 2 gamma minus 1. So you can take gamma 1.4 or then for air, so 1.33 also you can take. So accordingly I have calculated for 1.4. I do not see much difference and it will be around 7.41. I hope that you have all got this answer correct. Then you can refer to this formula in the book also, the derivation of this formula. So in this book Power Plant Engineering by P.K. Nag, I think the derivation is also given, so you can go through the derivation if you like. Then let us go to the next question, that was question number 12. There was a mistake actually in the question, but although the mistake was not quite significant, it was not reflecting quite significant error in the options. So the mistake was, or the correction to be made was, the compressor temperature, the air inlet temperature to the compressor, it was 10 degrees Celsius as it was given, but it should have been 20 degrees Celsius. So if you put this value, I think you will get the exact answer in the option. Anyways, the question goes as like this: gas turbine power plant generates 25 megawatt of electric power, and this is actually not quite needed in solving this problem, so it is just given as a fact. Then air enters the compressor at 20 degrees Celsius and pressure 0.981 bar and leaves at 4.2 bar, and gas enters the turbine at 850 degrees Celsius. So if the turbine and the compressor efficiencies are each 80%, determine the specific work of the turbine. So what we are given the inlet to the compressor temperature corresponding to this, then the inlet pressure is given, the outlet pressure is given, and the maximum temperature is given 850 degrees Celsius. So basically in all of these kinds of problems we need to calculate all the temperatures, the like T2s, then after that T2, then from T3 we can calculate the T4s. Using the efficiency of turbine we can calculate T4, and after that we can calculate what is needed, that is the specific work of the turbine. So let's see. So this 1 to 2s is a adiabatic reversible adiabatic process. So we can use this correlation, and according to this we will get the value of temperature at 2s, which is 443.9 Kelvin. And if you use the efficiency of the compressor, so that is efficiency is T2s minus T1, this divided by the temperature difference between 2 and 1, T2 minus T1. So accordingly we will get the value of 481.6. So you can see that so the process has deviated from reversible adiabatic to simple adiabatic with with heat losses. So as the heat is being lost as friction, and it is basically increasing the temperature of the steam, the air which is entering. So you can see that the temperature has risen of the air from 443.9 Kelvin to 481.6 Kelvin. So that is the entropy change that we are getting due to the entropy changes. Then for turbine, similarly, if we use this process T3 by T4s, and we can calculate T4s with this correlation, that is 741.25 Kelvin, and using the efficiency of the turbine again we can calculate T4. So that is 817.6 Kelvin. So finally the specific work of turbine is given as Cp into T3 minus T4. Specific work means the work done per mass flow rate of gas which is entering. So for our convenience we have taken the value of Cp as the Cp of air, because no other values were given, so you can assume that. And I think there is not much difference between the Cp of gas and Cp of air, just a 0.1 kilojoule per kg Kelvin, that is the difference. So you can directly calculate by using Cp of air and T3 minus T4, since only specific work of turbine is being asked, not the specific heat of the entire gas turbine power plant, where if we needed to calculate the entire specific heat, then we'll have to consider this work to be done to run the compressor. So there we will have to subtract this amount of work from the turbine work. So by that we can calculate the specific heat of gas turbine power plant as a whole. But now specific heat of specific work of turbine is Cp into T3 minus T4, that is this temperature difference, and that is equal to 306.93 kilojoule per Kelvin. So even if you have calculated it using 10 degrees Celsius, I do not think your answer would be deviating much from this value. So that was the question number 12. Then moving to a quite tricky question, 13 to 15, and it's a very good and tricky question. And so here basically what we needed to do was that okay, let me read out the question first. Steam flows through the nozzle with a velocity of 450 meter per second at a direction which is inclined at an angle of 16 degree to the wheel tangent. Then steam comes out of the moving blades with a velocity of 100 meter per second in the direction of 110 degree with the direction of blade motion. Then the blades are equiangular. We will use this property. Let me show. I will show you how. Then the steam flow rate is given as 10 kg per second. We need to calculate the power developed, axial thrust, and the blade efficiency. So the main thing here is how to get our velocity diagram. If we can get the velocity diagram, we can calculate everything. And here we cannot use the simple angle formulas to calculate this velocity diagram. We need to actually draw and calculate it, draw and get the velocity diagram. So first we are given that the velocity at inlet is 450 meter per second. The angle inclined of this inlet velocity is 16 degree. then the outlet velocity, absolute velocity, is 100 meter per second, and the angle at which it leaves out with respect to the blade motion, that is 110 degree. And what does it mean is that the blade motion, the blades will be rotating in this way, u will be directed in this way, and the from the blade the velocity will be coming backwards to the blade motion, right? So if the blade is moving from this right to left, then the due to the curvature of the blade, the steam will be leaving from left to right, in the direction from left to right, so it is a little bit inclined. So that inclination is given as 110 degree, and based on that we will be calculating the actual angle that we need. So I will show you how. So this is the velocity diagram. If you calculate, if you draw, you will get this kind of velocity diagram. So let me go through the procedure of how to draw such a velocity diagram. So here, so first we will draw v1. So first let us consider one scale. So 1:50 means we need a scale for only drawing this v1 tangent lines, na vectors, right? So v1 is 450. So if we use scale 1/50, so in a paper we will be needed to draw like 450 divided by 50, that is 9. So 9 centimeter. Okay, so this line will be of 9 centimeter. We can consider it as of 9 centimeter. Then v1 we will draw it inclined at an angle 16 degree. So first we draw v1, so this particular line, okay, at an inclination of 16 degree, that was given to us. Then we know that from this point we can draw the absolute velocity at the outlet, which was also given 100 meter per second. Okay, we know what is the what should be the blade velocity direction. The blade velocity direction is then in this direction. So basically this angle v2 is making with this horizontal in this angle, that is 110 degree, that is given. So you can correlate with this also. So I am just drawing a horizontal line out here. So this is interior alternate angles, right? So this is 110, exactly same angle here, it is 110 degree. And we are only the alpha 2 that we consider for analysis is this angle. So we basically subtract it from 180, so we will get alpha 2 as 170 degree. So this is the 70 degree that we are getting. Okay, and v2 is again 100 meter per second. So with the scale, if you are considering 9 centimeter to for 450 meter per second, then what it will be? It will be like 2 centimeter for v2 in the direction of 70 degree. So in the direction of 70 degree we'll be drawing v2 for 2 centimeter length. Okay, so this is 2 centimeter, this is 9 centimeter. So we have drawn the v1 and v2. Okay, then what we will do is that we'll find the value of vf1 and v2. So we know the value of v2 and v1. We know that this this component that is directed towards the axial direction, so that is the vf of each case. So this is vf1 with respect to this horizontal line, and this is vf2. Okay, we can directly calculate vf2 and vf1. Simply join this this point to this vertically, and similarly here also from this point to this line vertically. Okay, this is 90 degree. Then when we have found out vf1 and vf2, we need to now calculate the relative velocities, right? This relative velocities and at what angle these are inclined at. Now one thing we know from the this question, that the blades are equiangular, means if the relative velocity of means at the inlet, if it is beta 1, that will be equal to this the relative velocity which is exiting the blade, that is beta 2, right? Beta 1 will be equal to beta 2. So we just simply need to calculate the beta 1, right? So if this is beta 1, this is also beta 1, if we somehow produce vf2 the same length in the opposite direction. So from here, this length we have drawn here from this point to this point, this is equal to this. Okay, so then this triangle will be exactly same as this triangle, and this angle will be also equal to this angle. Now if this angle is equal, similarly this angle and this angle will be this vertically opposite angle, right? So we have created a triangle such a way that this angle is now equal to this angle. Hence we can, if we join these 2 points, this will be our VR1. So is there any confusion? It is a little bit tricky, but shall I repeat once more?
Understood, sir.
Understood. Okay. Now for relative velocities, we know that the angle, this beta 1 and beta 2, so these two angles are equal, right? So it is because of the fact that the blades are equiangular. Okay, so that is why the velocity, relative velocity at which it is coming inside the blade, that will be equal to the relative the angle at which it is exiting the blade. Okay, so VR1 inclination and VR2 inclination will be same. Okay, that is we got it. Then we know that if this is same, if we can produce the same triangle in the backward direction, then we'll again get this this angle equal to this angle, right? So if we are getting these two angles equal, then this means that this line is basically a straight line. If we join this particular line, this line, whole line, so this is basically will be a straight line, because this angle will be equal to this angle for a straight line condition. So by this we can affirm that yes, this VR1, if we join till here, this will be actually the relative velocity. So that is why we can draw it till here, this length of the vector, that will be the relative velocity which is inclined at an angle beta 1, which will be directly getting from this diagram. Okay, be it whichever scale we produce in, so that will be directly given. The scale is not needed for angles, it is only needed for the velocity vectors. So we will directly get the value of beta 1. So if we know the value of beta 1, so directly we will also know the value of beta 2, since beta 1 is equal to beta 2, right? So that is how we are drawing the velocity vectors, but we do not exactly need the velocity vectors in solving these 3 options that we are having. But we need this particular point at which it is coinciding with this horizontal line, because this particular point, when we are observing, so this distance, that is the blade velocity, right? If we do not know where this position, where this point coincides with this horizontal line, we will be unsure about the velocity. So so we need to first calculate the relative velocity which is coinciding at this particular point. After that we'll get the blade velocity from here. So by measuring the blade velocity from this diagram, okay, we will just put a scale and measure this particular length, and directly multiplying it with our scale, we'll get the tangential velocity to be 167 meter per second. So this is how we have got the tangential velocity 167 meter per second. We have got the flow velocities, right? We have got the flow velocities, and other the world components and everything will get directly from here. There is no issue. So we just needed this blade velocity for now, because the flow velocity can be directly given as the cosine, the sine of v2, and the means the difference between the sine components of v1 and v2, right? So we have the angles already with us, we could have directly got without drawing the velocity diagram. Again, the world components, so for world components this cosine components of v1 and v2 are required. So we could have directly got without drawing the velocity diagram, but the drawing of the velocity diagram is quite necessary, because we need to calculate the power developed, and for power developed, the formula, we require the blade velocity also. So in order to only calculate the blade velocity, we have to go through so much of trouble, right? So that is why we draw the velocity diagram, and we got the blade velocity as 167 meter per second. So is there any confusion remaining in how the velocity diagram is being drawn? Okay then, so let us move on then. Now, as I have already talked about the world velocity component, so the world velocity component is the summation of the cos alpha and cos means the absolute velocities v1 and v2 cosine components. So the plus indicating that it is to in the same direction. It is both contributing to the means the rotation of the blade in the direction of the blade. So that is why we are adding it up, and together we have got 466.77 meter per second. And you can directly also calculate, since we have already calculated this, we do not need to calculate it again by the cosine component. We can directly measure the length of the horizontal line. So this line from point A to this point here, so if we calculate the horizontal distance, we will directly get, and multiply with the scale, we will directly get the value of the world component. So from this we have developed calculated the power developed, which is mass flow rate into this world component and into the blade velocity. So that is equal to 780 kilowatt. So we require the blade velocity out here. That is why we have drawn this whole diagram. Again, the next part is we need to calculate the axial thrust. So for axial thrust, we need the axial velocity component, that is v delta vf, that is v1 sin alpha 1 minus v2 sin alpha 2, and together it is 30.1 meter per second. Or we can simply also calculate this length. Okay, so we draw a horizontal line out here and we measure this difference. So this difference will be multiplied with the scale, we will get 30.1 meter per second. Then after this, the axial thrust is equal to m into delta vf, so that will be equal to 301 Newton. The last part is to calculate the blade efficiency. So for that we have to know what is the total energy which was with the steam at the inlet, so the total velocity will be the kinetic energy of the steam at the inlet, that is half mv1 square, which will be equal to 101 point, sorry, that is 1012.5 kilowatt. So this is the total available energy with the inlet steam, and out of that how much is utilized, we have already calculated it for the power developed case. So we'll simply take the ratio, and this is the total percentage, 77% of the total inlet steam which has been used for driving the work. So that is the blade efficiency is 77%. Okay, so from this we have covered the problems which were present in assignment 4, and is there any doubt till now? Hello? Is there any doubt till now, or am I getting too fast?
No, sir. No, sir.
Okay then. So now I'll
I'm
be
taking screen.
okay. So you need not take the screenshots. I will be uploading this PDF document in the website, so no issues.
Yeah, okay then, sir.
So
I'll
now
complete tonight.
so next I'll be talking about this the theory part, which will be required by you to solve this assignment number 7, which is due till 14th, I think, na 14th September. So so here we have basically two components, the wind turbine and this solar energy. So these two are compromising maximum of the questions of this assignment 7. So first of all, I would like to cover the wind turbine part. So basically there are two types of uh, two categories of wind turbine which was mentioned. The first is the horizontal axis wind turbine, which will be used in most of the question, in all of the questions it is being mentioned, the horizontal axis wind turbine, or HAWT, it is also referred as like that. Then and the another category is the vertical axis wind turbine. The difference between these two is that you see the rotation in which, along the which axis it is rotating, the blades are rotating. So these are the blades. Okay, so these are the blades, it is being rotating along the axis which is in horizontal direction. That is why this is called as the horizontal axis wind turbine. And in the vertical axis wind turbine, the axis is in the vertical direction, and the blades, so these blades you can see, these are rotating in the along the vertical axis. So there can be various designs of blades. So and these blade designs are basically very crucial for the speed and the power development. So let us understand a little bit in depth how this blades are being rotated, or how this blade design is influencing the power development. So for that we'll have to talk means the direction of the wind, how it is striking the blade. And basically our blades are having this aerofoil type shape. You can see this aerofoil type shape means it is a little bit curved towards where the towards the side, means in the direction of the velocity. So if the blade is to move from bottom to top in this direction, so this will be a little more curved and this will be less curved. Okay, this is the relative wind which is coming at this direction. Let us assume it to be horizontal, and horizontally it is striking this. Then there is a concept called as the angle of attack. So angle of attack is basically the angle between this relative wind direction and the chord of this aerofoil. What is the chord? Chord is the extreme left position and extreme right position when these are joined by a particular line and it is extended. Okay, so chord is the line which is joining these two particular points, and this chord line can be extended in this same direction, and by that we can calculate the angle of attack. So this is the angle of attack, you can see. Okay, so what happens is that when the wind as it flows through this aerofoil, what happens, since this is more curved, so the circumference or the length that a particular means the air particles will have to move is high at the top position, and in the bottom position the curve is less, so the air particles will have to move a little bit lesser distance compared to this upper position. Now we know that according to conservation of mass, and the mass of air which is entering at one side will also have to leave at the other side at the same time, right? Otherwise there will be a reduction in the mass flow at each sides. So that is why what happens is that the air particles which has diverged in the upward direction, and since it is having a larger distance to travel, so it will have to move a little bit quicker to reach this point at the same time. So that is why the velocity in this curved region, it is increasing, it is higher than compared to here, right? Due to the conservation of mass. So as the velocity here is more, by Bernoulli's principle we can say that if the pressure head and the velocity head and the potential head, we are not we are having at a equal this jet direction, so we will not be considering the last head, the potential head. So basically the pressure head and the velocity head, so that will remain constant as per the Bernoulli's equation. So here, as the velocity is high, so the pressure will be low as it needs to be constant. Again here the velocity is low, the pressure will be high, as it needs to be constant. So here it is having higher pressure at the bottom, and here it is having lower pressure at the top. So the pressure direction is from bottom to top. So this pressure difference is actually rising the airfoil and contributing to the rotation of this particular turbine blades, like you can see here or here, right? So that pressure difference is causing the lift. So it is also called as the lift force. And there's another component, that is drag force, which is not contributing to this, means negatively impacting this rotation, but we will be not discussing too much depth into the aerodynamics. But simply, if you can see that as the wind approaches and impacts on the aerofoil, it is having a particular angle of attack, and this angle of attack is due to the mass of conservation of the conservation of mass and the Bernoulli's principle. We can see that the pressure difference is causing the blades to rotate, right? So here till now we are clear that how the rotation is happening of the blades. Now the lift force that I was talking, the pressure due to the pressure difference. So as per the angle of attack, you will be thinking that as we are increasing the angle, so at higher angles always this lift force will be high. But actually in if you go through the aerodynamics of this airfoil shapes, you will see that the angle of attack, as the increasing angle of attack, with increasing angle of attack, the lift force, it increases up to a particular point and then decreases. So that is why there is an optimum angle of attack that we can see here, optimum angle of attack. So beyond which will be so we'll be not getting the optimum lift force. Okay, so the lift force rotates the turbine blades, and it the changing of the angle of attack changes the lift force and the speed. So the lift force is also contributing to the speed of rotation. That is why changing the lift force will change the speed of rotation. So till now we are clear that how the angle of attack is changing the means the lift force and the speed of rotation. So this is one angle, this is angle of attack. Next we'll be talking about some other angle, but before that let us talk about the coefficient of performance. So each turbine, we will have to rate the turbine according to its performance, right? So this is one of the parameters that is called the coefficient of performance, and it is given by the power developed by the turbine divided by the total power available. So the total power which is contributing to the rotation of the turbine blades divided by the total power available. So total power available is the kinetic energy of the air which is striking the blades. Okay, so that is the coefficient of performance. So here I have taken a screenshot from this book by P.K. Nag, that is Power Plant Engineering. So here you can see that this is the curve that you can see. This is the plot between the coefficient of performance along with the tip speed ratio, which is the blade ratio versus the velocity of the incoming air. Okay, so as we increase the tip ratio for an ideal rotor, the coefficient of performance always monotonously increases. But for actual cases, for this multi-blade, Savonius, Dutch, propeller 2-blade, then Darius 3-blade, so for in these kinds of turbines, there is an optimum coefficient of performance. So means there is an optimum tip speed ratio for which the coefficient of performance is the maximum. So that actually depends upon what? The tip speed ratio, and the tip speed ratio is basically the ratio between the blade speed and the velocity of air. So blade speed, the speed at which we are rotating the blades, it is also impacting to the coefficient of performance, right? Again, as we have already learned, the speed at which the blades are rotating, it is dependent upon the angle of attack or the angle at which the wind strikes the blades, right? So the angle at which strikes the blade is now impacting the coefficient of performance, right? So it is having a very great significance, and it is also impacting the load at means the power generation, so how much power we are needed to generate. So if we are having higher this suppose I will give you an example. Suppose the v infinity, so it is not remaining the constant throughout the day. Suppose the v infinity, it increases, it decreases accordingly. The tip speed ratio, it also varies. So we will have to modify this blade speed in order to make the constant tip speed ratio. If we meaning the angle of attack, we'll have to change the angle of attack, right? That is why we means the engineers, they give another mechanism. Okay, first of all, let me talk about the power available. So this is the power available, the kinetic energy of the whole air, and this is basically what I have told about uh, the rotation power, that is Cp into Pt, electrical power, the conversion factor, efficiency of conversion into the rotation. So not all the rotating energy, it is being converted into electrical energy because of the friction losses and everything. So now let us move on, as we know that we need to change this u. So now I have already told about that the u, we need to change the u with varying velocity conditions, right? So the wind speed may not remain the constant throughout the entire day. We need to change the angles. So changing the angles basically means pitching. So pitching means the aerofoil which is attached to the hub. Okay, you see, if this is the horizontal axis, about the horizontal axis the blade is rotating like from bottom to top. Okay, so for this kind of arrangement, there the aerofoils or the blades are hinged to the hub, and it is we can through some mechanism we can rotate this aerofoil or the blade, okay, at particular angle. The angle at which we are rotating, that is called the process is called as pitching, or the pitching angle that we are implementing. So this is beta, is basically the pitching angle. So what it does is that by introducing the pitching angle, it changes the effective angle of attack, right? How it is changing the effective angle of attack? So if we increase the beta, okay, if so the wind speed direction is constant, so if we rotate it a little bit towards this direction, okay, now the chord line is like this, so the angle of attack is now reduced, right? The and now since angle of attack is reduced, it will be giving a different blade velocity, and with the different blade velocity we can attain the constant tip speed ratio. Okay, this is only done to attain a constant tip speed ratio, so that is called as the pitching. Okay, so these are two angles which are associated with pitching, and together we can see that tan alpha plus beta equals to u by v infinity, where the alpha is the angle of attack and beta is the pitching angle. So there are maybe one question which is related to this pitching. So I think from this theory you might be able to solve that problem now. Okay, and other problems also, I think I have covered almost entirely all the theories which will be needed for the assignment as well as the later on the test. So this was about the wind turbine. So if you have any doubt, please ask now. Is there any doubt? Okay, then if there is no doubt, then let us move on to the solar cell characteristics. So this is not quite often observed for a mechanical engineer. This is more towards the electrical and electronics part, right? But we need these characteristics in order to efficiently convert the solar energy and means get the electrical energy from the solar energy for the efficient conversion from this solar to electrical energy. So that is why we need to understand what is the solar cell characteristics or photovoltaic cell characteristics. So the characteristics means is the particular chart between the current and the voltage. Okay, so this is how the solar cell characteristic looks like, and the direct means the value of Im, it can be positive or negative depending upon the is there any doubt? Hello. Okay, so as I was saying, the value of the this Im or the current can be positive or negative depending upon what kind of this diodes that we are semiconductor diodes that we are using. It can be NPN or this PNP. So accordingly, the characteristic will change, but the basic concept remains the same. That this is the short circuit current, which will be always higher than this maximum Im, maximum current that we can obtain from this the solar cell. Then this is the open circuit voltage, which is the maximum possible theoretical voltage, and always the maximum amount of voltage that we can obtain from the solar cell, it will always be less from this theoretical maxima, right? So what is short circuit current? So short circuit current is the largest current which may be drawn from the solar cell. So basically in a solar cell there can be resistances. If there is no resistance, if we assume that there are no resistances when the carrier charges are moving from the valence to the free band, so then the current that we'll obtain is the short circuit current. So that is the maximum we can derive theoretically, but it is not means attainable in physical means not feasible to attain this. Then we have the open circuit voltage. Let me talk about open circuit voltage first. So open circuit voltage is the maximum voltage that can be obtained. So that is the potential difference across the load when it is not in connection. Okay, so that is the maximum voltage, and if the load is connected, there will be some resistance losses. So potential drop, right? So for this potential drop, the voltage that we obtain is always less than the open circuit voltage. So these are the theoretical maximas. Then we have the reverse saturation current. So this concept is later on to be used. Okay, so where it is used, uh, so there is a relation between current and voltage obtained from solar cell. The expression goes like this: I equals to, that is the current which we are getting out of this solar cell. So that is ISC minus I naught into exponential of EV. So V is the voltage we are obtaining. So I and V we are obtaining from the solar cell, divided by K into T. So K is the Boltzmann constant and T is the temperature in Kelvin, minus 1. So here we have another term, IO. So this is called as the reverse saturation current, so which is a part of the reverse current in a semiconductor diode, and is caused by diffusion of magnetic carriers from neutral regions to the depletion region. So there are major carriers and magnetic carriers. So means if we go a little bit deep into this electronics, so when a semiconductor diode operates, so there is a exchange of carriers. The majority carriers, it basically contributes to the current that we are obtaining, okay, at the end. But there are some means diffusion of magnetic carriers in the opposite direction of the current that we are getting. Okay, it is the flow of these magnetic carriers. So carriers are basically holes and electrons, right? So the flow of these magnetic carriers, the current which it is causing, okay, so you must be knowing that electron the direction of the electron flow, the and the direction of the current, it is in opposite, right? So and the hole which is imaginary, so the direction of the movement of the holes, so it is basically representing the direction of the current. So these are the carrier movements. So corresponding to this carrier movement, there is some current which is associated with it, right? So due to this, some magnetic carriers are present which are flowing in such a direction that the net current that we are obtaining is being reduced. So that is the magnetic areas. So this reduction in value is due to this I naught. Okay, so that is called as a reverse saturation current. Then, so if we have understood this, then during a short circuit, okay, so during a short circuit, what will happen is that the current will finally will be 0, and the current obtained here will be 0, and the voltage will be open circuit voltage. So the voltage, this open circuit voltage, if we put in this particular equation, then we will get the value of this open circuit voltage as this. So we have got the theoretical maxima of this at this particular point. Okay, then the power, it is always calculated as V into I. V equals to this expression. Okay, but we are mainly we are more interested in knowing the maximum power, that is PM. So let us go through the derivation of how the PM is being calculated or derived. So for maximum power, so we can differentiate the power that we're having with respect to V and I. So for getting the maximum voltage, means the voltage corresponding to which the power will be maximum will be this dp by dv equals to 0, and correspondingly the value of Vm, if we solve it from this particular equation, we'll get the maximum power. Then similarly, if we solve it for current, we'll get the maximum current as this. So normally what we do is that we get the value of this current, the maximum the current corresponding to the maximum power. Then we derive the maximum power as this Vm into Im. So this is a basic formula, and as a hint, I can tell you that the assignment questions can be solved with this formula itself. There's no trouble with that. So you can try back home to solve this assignment question 13 to 15 with this particular theory. Then you can again.
Excuse me, sir. 1 minute, sir. Sir, in question they asked find the maximum possible power output. Which is that one, sir?
You tell me.
Possible power output means.
You tell me. So that is maybe I have explained that here. You just go through the theory once again, and I am sure that you will get to know about it. There is maximum possible power output and maximum obtained power output. So what is the difference between these two? I think I have explained quite well here, or maybe I will be explaining later. You just
Okay, sir.
you just have some patience. I like your enthusiasm, but please have some patience and see this. Okay, you will get the answer yourself.
Okay, sir.
Okay, sure. So this is the maximum power here. Now I'll be talking about as you have told, the maximum power output. Okay. So before that, let us come to this concept, the fill factor. The fill factor is equal to the ratio of the maximum obtainable power by ISC into VOC, the short circuit current into the this open circuit voltage. So that is basically the maximum obtainable power is Im into Vm. So maybe I have answered one of your questions. So maximum obtainable power is the means the power Pm, right? In this graph, Pm is the maximum obtainable power. So corresponding to it, what are my current values? That is Im and Vm, right? So Pm equals to Im into Vm. So this is the maximum power that I can take from this solar cell, not more than that. Okay, but what is my limit? My limit is what is the theoretical maxima of current into the theoretical maxima of voltage. So theoretical maxima in a particular solar cell, that will be corresponding the theoretical maxima of current, that will be short circuit current, and the theoretical maxima of voltage, that will be open circuit voltage. So the product of these two will be the theoretical maxima of the power that can be derived, but it is never possible. because of resistance losses, right? So that is my theoretical maximum. So the fill factor is basically a measure of the quality of solar cell, because it is telling us the ratio of how much the maximum power can be obtained versus the how much is the theoretical maxima. Then the fill factor is directly affected by the values of the cell series, shunt resistances, diode losses. Yes, sure, that is why we are getting less than 100%. Then higher the fill factor, greater will be the efficiency. Yes, more closer we will be going to the theoretical maxima. The interpretation of this fill factor can be as such that the measure of how close the cell's output power is to the theoretical maximum, how close we are getting the power output to the theoretical maxima, that is basically designated as a fill factor. So typical fill factors, these are 50% to 82%, and the fill factor to a normal silicon photovoltaic cell is 80%. So these are basically a few facts. So the theoretical maximum possible power output, that is ISC into VOC, and the expression of the maximum efficiency will be the maximum power that we can get divided by IT into AC. So what is IT? IT is the total heat flux falling upon a surface. So when we indulge in all this electronics electrical thing, let us not forget our base. So from where are we deriving this electricity? This electricity or the current we are deriving is from the heat flux which is falling upon the surface, the solar cell, right? The heat flux from the sun, or the radiation, the total radiation which is falling upon this cell. So that is the heat flux, that is denoted as IT, which is having the units watt per meter square, and the area of the collector AC. So area of the how big is the solar cell, so how many this semiconductor diodes are active, and actively these are receiving the incoming radiation. So that is denoting the area of the collector. So IT into AC, which will be the power, right? And IM into VM, it is also the power which is derived the electrical power. So the um, so again IM into VM, so that is again can be converted into fill factor into ISC into VOC. So as high as means the fill factor we are having, higher the efficiency we will be getting. So that is this particular statement out here, right? So this was about the solar cells, and I think by this I might have answered your questions, right?
Yes, sir. Sir, can you show the slide before to this slide, sir?
You will get the
Maximum power
slides.
slide.
You will get the slides. There is no issue. I will be uploading them to the drive. So are you getting no access to these drives?
No, no, sir, getting, sir. Because now I solved two questions and now I am solving for maximum power. That's why.
This slide.
Yes, sir.
Okay, good. So this
Sir,
was about
maximum power formula that in one box.
maximum power.
That formula is there in box that one only, sir.
This you can verify from the both ways. Hmm.
Find maximum possible power output.
Hmm.
Okay, sir.
Okay.
Sir, thank you so much, sir.
Welcome. So we have come to the end of this session, today's session. So in the next session, which probably will be the last session, and I'll be discussing about the final this assignment, the theory regarding that, and maybe I'll be solving out the problems of this assignment number 7. So also I think there's no need to separately issue the PDFs for all the assignment problems, as I have already discussed everything in my videos, right? So you can directly go through the presentations and you can go through the videos to get to know about the solutions of the different problems in the assignments, right? So by this we have come to the end of this session. Thank you, You may now leave. And if you're having any questions, please.
Sir, this month, 25th Sunday only, we have exams, sir, final exams.
Okay.
This power plant engineering final exam is on 25th Sunday.
Right. And when do we have our next session?
Next session is today
17, no?
17, sir.
So you can ask me other questions also during that session. I may be able to help you out, so you can revise about that.
Because in assignment number 8, no, same 13, 14, 15 questions are something not relevant to it, videos which I have explained in the course.
But there is one thing, you cannot rely completely on the video. So the videos were only of 30 minutes. So how can you expect that the professor will be able to explain you all the theory related to those all the concepts, right? So you will have to explore a little bit. Okay, go through a little bit more, go through the books, and I'm sure, as I have got the theories regarding that, you will also get the theories, right? You will have to think a little bit, right? Yes. Okay then. So is there any more questions?
The hall tickets when they will give, sir?
Which one?
The hall ticket generation link. Admit card link when they will upload, sir?
Regarding that, I do not have any information, so I'm just here to teach. So regarding that, you may directly contact to the NPTEL.
Okay, okay.
Okay.
Okay, sir. Thank you so much, sir.
Okay, welcome.
Today I got maximum 4 to 5 solutions in this today's lecture.
Okay, I'm glad to help you out. Welcome.
Yes, sir. Sir, in next session, will you explain assignment 8, 13, 14, 15 means the same, some theory regarding that, sir?
Sure. I will try to do that.
Yeah. Okay, sir. Thank you so much, sir.
Welcome.